Hello and welcome back to another video. In this problem, we're told in the theory of relativity, the Lorentz contraction formula, L equals L naught times the square root of 1 minus v squared over c squared, expresses the length L of an object as a function of its velocity v with respect to an observer, where L naught is the length of an object at rest and c is the speed of light. We're asked to find the limit as v approaches c from the left of L and interpret the result. And we're also asked why is a left-hand limit necessary. So the limit as v approaches c from the left of L is the limit as v approaches c from the left of L naught times the square root of 1 minus v squared over c squared. So just plugging in 1 minus c from the left squared over c squared. I think it's helpful to do it this way because this isn't a calculation we're doing, right? It's not literally a calculation to calculate c from the left, but we have to understand what actually is going on here in calculating it. So we have L naught times the square root of 1 minus this fraction. Well, what is this fraction? Well, we're taking values that are slightly less than c, right? And we're squaring them. So this is like we take 2 squared and it's 4. Now take a number that's slightly less than 2, right? We don't know what it is, but we know it's slightly less than 4. So we can think of this as c squared from the left over c squared. This is L naught times 1 minus. Now we're taking values that are very, very slightly less than c squared, and we're dividing them by c squared. So this is like 1.99 over 2. C squared over c squared is 1, but the numerator is ever so slightly smaller. So we're taking values of 1 and we're approaching them from the left. So this is equal to the square root of 1 minus 1 from the left. Well, what does that mean? Well, this is like we've done our division, and we get a number that's very, very close to that's very, very close to 1, but it's very, very slightly less than 1. So now, if we're taking 1 and we're subtracting this number, we're getting a number that's very, very slightly greater than 0, right? Because 1 minus 1 is 0, so we're approaching 0. And since we're subtracting a very, very slightly smaller than 1 number, the difference is going to be very, very slightly larger than 0. And therefore, we are taking the square root of numbers that are very, very close to 0, which means that we are just approaching 0. And again, it's from the right, not the left, which is good because we can't take the square root of a negative number. So we can just think of this as L naught times numbers approaching 0, which means we're just multiplying by 0 basically. And L itself, as v approaches c from the left, approaches 0. So this means that as v, the velocity with respect to an observer, as this velocity approaches the speed of light, the length of the object appears to shrink to nothing. Where if an object passed you at the speed of light, it would appear to have no length at all. Why is a left-hand limit necessary? For 2 reasons. There's the math and the physics. So the physics side is if we were approaching from the right, that means we'd have velocities that are greater than the speed of light, and you can't have values that are greater than the speed of light. And the math reason is that we'd be not approaching 0 from the right here, we'd be approaching it from the left, right? If we did all these calculations with the opposite sign up here, we'd end up with the opposite sign here. So you'd be taking the square root of values that are slightly less than 0, and you can't do that because you'd be taking the square root of a negative number. So for the math reason and the physics reason, a left-hand limit is necessary, but we do know that the limit as v approaches c from the left of L is 0.